Welcome back, folks. In today's class, I'll be talking about the energy. And if I look into the definition of energy, it is the ability of our body to do work. Now, the simplest example of this will be we human being eat some food, and thus we've been able to do work. We've been able to run, we've been able to walk, and we've been able to lift something. That's because we consume something. Food goes in our body, and because of that, energy is produced. And then by walking, by running, we consume that energy. Now, there are different types of energies. So, one is potential energy, another is kinetic energy, then spring energy, and then there is work. Work is also a form of energy. And then there is renewable energy, sun energy, heat energy, heat, you know. So these all are various forms of energy. I've written some of these, but there are a lot more than these. One of the main thing about the energy is, if I look into the first law of thermodynamics, that energy can neither be created nor be destroyed. It can only be converted from one form to another. That's the definition of first law of thermodynamics. What does this mean? That if you have certain form of energy, let's say this is a this is a ball placed on top of a cliff. Now, what kind of energy this has? This has potential energy into it. Now, potential energy is equal to mgh. And potential energy, I'll give you a briefing about what potential energy is also before diving down into the first law of thermodynamics. That the energy contained in a body by the virtue of its height. And this object, because it's placed at a height, so it has potential energy that is equal to mgh. Potential energy is mgh. Now, once you're going to throw this ball in the downward direction, that potential energy will convert into kinetic energy. Kinetic energy is what? Kinetic energy is the energy possessed by an object because of its motion. Now, as the ball drops in the downward direction, the ball starts moving. So what's happening is that potential energy is converting into kinetic energy. Let's say this ball has 10 joules of potential energy when it is placed on top of a cliff, and the ball is not moving when it is placed on the top of a cliff, so it has the zero kinetic energy. Now, potential energy, as soon as it starts moving, let's say it reduces to 9 joule, so it will have 1 joule of kinetic energy, 1 joule. It then it moves further down, the potential energy reduced to 8 joules. This will change to 2 joules of kinetic energy. And when the ball is about to hit the ground, just about to hit the ground, it will lose all its potential energy. Again, mark my words, in physics, the wording is really important. I'm saying it's just about to hit the ground, means it is ever so close to hitting the ground. So thus I can assume that potential energy is zero at that time, and kinetic energy will be 10 joules. Lot of students think that, okay, they start finding the potential kinetic energy once it hits the ground. After that, that will be a wrong assumption. We always take that it is about to hit the ground. At that time, what is the kinetic energy and what is the potential energy? Okay, so and in this case, what's happening, if I see it carefully, that all the potential energy it had is converting into the kinetic energy, and that's in accordance with the first law of thermodynamics, that energy can neither be created nor be destroyed. It can only be converted from one form to another. And that happens with we human beings also. If I consume something, only then I can walk. If I'm not going to eat something for 10, 15, 20 days, I won't be able to walk. I won't be able to run because my body will be deficient of energy. So What does food do? Food has energy which our body processes, and thus I can convert it into the kinetic or potential or whatever form of energy you wanted to convert while doing any specific work. So hopefully you understand the concept of energy and the first law of thermodynamics. Now keeping forward, in our syllabus, we will talk about potential energy, kinetic energy, and spring energy and plus work. These are the four forms of energies which we'll talk about. So I'm gonna start with the work. Work. If I look into the definition of the work, work is again it's a form of energy. Form of energy. It doesn't tell me this definition. But if I look into the mathematical definition of work, that tells me a lot. Work is equal to force times distance moved, distance moved in the direction in the direction of force applied. Direction of force applied. Now, why I've specified in the direction of force applied? Because if this is a bag or this is a box which is placed on a ground and you're applying force at an angle, you're standing here, you're trying to lift it or move it, shall I say, in the forward direction. The box, you're trying to move it in this direction and you wanted to find the work done. In that case, the force is being applied at a certain angle compared to the direction in which the body is moving. Thus, I have to consider the angle in that scenario also. So the full formula for the work is force times distance moved times cos of theta. So I have to take this angle theta also. So if you wanted to visualize this, it should always be if the object is moving in this direction and I wanted to find out how much work is done to move the object to a certain distance, let's say 10 meters, then I have to apply the force in the same direction. They both should be in the same direction, parallel. So if the force applied now is 10 newtons and then object covers a 10 meter of a distance, then work will be equal to 10 times 10, which is 100 joules. The unit of energy is joules. And the unit of not only energy, the forms of energy will also be the joules. So potential energy, kinetic energy, spring energy, or work, heat, sun energy, all these energies, we will talk about the SI units, which is joules. Now, another thing which I want to talk about in this case is, let's say if you are applying a force at an angle of 30 degrees, let's keep it simple, or 60 degrees. 60-degree will be simpler for me. So this is 10 Newton, and then you move it to a distance of, let's say, 5 meter this time around. So I'll use the formula work equal to force times distance moved times cos of theta, and that will be equal to force applied is 10 newtons, distance moved is 10 newtons, distance moved is 10 meters, shall I say, and cos of 60 degrees. Cos 60 is 0.5, this is 100 times 0.5, and work done will be equal to, well, actually I took it as 5 meters, so I should write down here 5. So this is 50 times 0.5, which is 25 joules of work has been done, or 25 joules of energy has been consumed. So hopefully you got the basics of works. Now I'm going to talk about a couple of math problems on the work. Here, a work acts at an angle of 30 degrees relative to the direction of the displacement. What force is required for 9600 joules of work over a displacement of 25 meter? So we're going to write down the formula force equal to not the force, I should write it as work is equal to force times distance moved times cos of theta. That's the work. Now, force is what we are looking for. Force acts at an angle of this. What force is required? So this is what we are looking for. Distance moved is 25 meters and cos of 30 degrees, and work in this case is 9600 joules. So what I'm going to do is I'm going to try and find out the cos of 30 degrees. Make sure your calculators are in the degree mode, not in the radian mode, because it is given to us in degrees the angle is. And so this is 0.866 times 25 times force 9600, and 25 times 0.866 is equal to 21.65 times force, which is equal to 9600, dividing both sides by 21.65. 21.65, I cancel this out. So this is 9600 divided by 21.65, which is equal to 443.3.41. Shall I write it? 41 newtons. That is the force applied. Okay, so let's look into another question similar to this one. In this question, a force of 640 Newton does a work of 12,500 joules over a displacement of 24 meter. What is the angle between the force and the displacement? Now we are asked to find the angle. So again, I'll write down the formula for work, which is equal to force times distance moved times cos of theta. And force is given to me 640 newtons. 640, distance moved is 24 meter, 24, and cos of angle which we are looking for, and then this is 12,500. Now I'm going to multiply 640 with 24. That will come across as 15360 cos theta 12500, dividing both sides by 15360. 15360 cancels out, and now 12500 divided by 15360, that is 0.81 equal to cos of theta. Now what I'm going to do, I'm going to take the cos on the other side. That's going to become cos inverse of 0.81 equal to theta. And the second function, cos inverse 0.81, that is 35.9 degrees of the angle. Again, make sure your calculator is in degree mode, otherwise your answer will be in the radians. So hopefully you understand the concept of work and how you can approach these questions. The main idea is this is the standard formula which we need to take care of. Now I'm going to move to the uh, other sections of the energy. So this is what we were talking about, that the different forms of energy. Work, we've talked about this. Now we'll talk about potential, kinetic. I briefly talked about initially, but I'm going to talk about it in detail now, and then later on we're going to move to the spring energy. So let's dive into the potential energy concept. So potential energy. Potential energy is the potential energy is the energy possessed by the object because of the height. So if this is a cliff, object is placed on top of the cliff, it has certain amount of potential energy with respect to the ground. It's really important that from where we are finding the potential energy. So for example, if this is a cliff, another cliff, and the ball is placed on top of this cliff, and I wanted to find out the potential energy possessed by this object with respect to the top of the cliff from here, then the potential energy value will be different. Let's see how. The formula for potential energy is mgh, which is mass times gravity times height. Again, we won't take the negative g value in this case as it is. So we will take, but later on. So for the timing, I'm just keeping the uh, numbers. And energy, one more thing I didn't discuss initially, energy is not a vector quantity, it is a scalar quantity. Yet we do talk about the directions, that is separate, but we'll talk about it. I don't want it to deviate from the concept which we have on our hand right now. So let's look into the potential energy, which is mgh. And let's say the mass of the ball is 1 kg, and the gravity force, just for the simple calculations, I'm going to use 10 meters per second square. Again, this is I'm using so that I don't have to use the calculator, but g value on the earth is 9.81. So 1 times 10 times height, let's say this is 2 meters, so this will come out to be 20 joules, all right, with respect to this ground. Now, with the ball is placed here, with respect to this place on the top of the cliff where the ball is, what is the height? The height is 0. So potential energy value in that case will be again mgh, 1 times 10 times height is 0. So the potential energy in that scenario will be 0. Make sense? So this is really important to understand. Now, in the same case, if I wanted to find out what is the potential energy on the ground, now what you are doing is you are covering the displacement in the negative direction. So this displacement is in the negative direction. So I wanted to find it here. So potential energy at the ground, if I take this as the reference point from here, while moving to the ground will be how much? So 1 times 10 times this height is -2, assuming this height is 2 meters. Okay, but the ball is moving in the downward direction. So potential energy value will be -20 joules in that scenario. It means this negative means that energy has lost from the system. 20 joules means the object has gained 20 joules with respect to the ground. So initially it's the way to look at it is that ball was here, you placed it on top here, now you wanted to find the potential energy. That ball has gained the 20 joules of potential energy. In this case, ball was here and you dropped the ball here, so ball has lost the 20 joules of energy. Make sense? In this, the ball has gained. In this case, the ball has lost. Negative means. So hopefully you were clear about the concept of potential energy. Now, with that, I'm going to talk about the kinetic energy also. So as I said, the kinetic energy means the energy of a body because of its motion. So if this is a car which is moving in the forward direction, it is moving. The word I used is moving. So it will have kinetic energy, and kinetic energy will, the formula for kinetic energy is half mv square. And let's say the mass of this car, just again for the sake of argument, I'm using the simple numbers, 100 joules, not the joules, 100 kg, and the car is moving with 2 meters per second. 2 meters per second. What is the kinetic energy? So half times 100 times 2 square, that will come out to be 100 times 4 divided by 2, that will be 200 joules of kinetic energy this car will possess. So hopefully you were able to understand the concept of potential energy and kinetic energy. Again, the direction does not matter because energy is a scalar quantity, it is not a vector quantity. So hopefully you were able to understand all these concepts. I'll see you in another lecture where I'll talk about some more problems on potential and kinetic energy, and then also I'll talk about the spring energy. So good day, bye.